Thanks very much. Thank you all for being here. It's great to be at IPAM. I'm going to talk about differential privacy first, and I want to save a few minutes toward the end to talk about the use of differential privacy in the disclosure avoidance system in the 2020 US. There are two kinds of data analysis. When we talk about privacy-preserving data analysis, there are really sort of two kinds that people look at. There's statistical understanding of the population as a whole. So, for example, and this was from the start the motivating example in the context of census. But you could also consider analyzing loan data for evidence of systematic discrimination, or even privacy of samples in machine learning, where we might want to be examining cells to try to learn to distinguish healthy cells from cancerous cells. And these cells in here are actually, they're healthy, but they're starting to become deformed because of the chemicals that are being produced by the cancer cells. So this is the first kind, sort of statistical, trying to learn about the thing as a whole. The other kind of data analysis where privacy is relevant is a kind of finding a needle in a haystack, as in the old Total Information Awareness program that was supposedly aimed at finding terrorists. Now, differential privacy is appropriate for the first kind of privacy-preserving data analysis, understanding the population as a whole. It is the wrong technique for the second, the finding a needle in the haystack. I do not know how to solve that problem with any kind of privacy, but we're talking about statistical analysis. Okay, so statistics. Statistics feel private. A statistic is a quantity that's computed from a sample, and it tells us about the population as a whole. This is why the field of statistics works at all. So if we had two data sets that were collected independently, but using the correct statistical procedures, and they're collected independently from the same large population, even if those data sets don't intersect, we expect that they're going to tell us the same things about the underlying population, about the population from which they're drawn. Again, that is why the field of statistics works. So my feeling is that the sense of privacy of a statistic is derived from exactly that fact. And you could also sort of think, well, nobody knows I'm in the sample, or I could claim I opted out. And somehow or other, especially because of the two data sets view, this statistic is not about me, it's about the population. So statistics feel private, and this is on the right track, but they don't by themselves give you privacy, and so they need some kind of help, and differential privacy provides this help. And in fact, differential privacy preserves the I could have opted out semantic sense of privacy for every computation, including total population counts, where we're not even choosing a subsample. So, how do we go about trying to study privacy-preserving data sets? Well, first we have to, privacy-preserving data analysis. First, we have to abstract the problem. So here's our abstraction. We have a data analyst and a database. And the database, or sometimes I call it a data set, has lots of good, juicy information. It's what we want to analyze, it's what we want to understand, but there's a privacy concern. Now, the analyst in our abstract version is going to get to ask questions or queries or conduct studies on the data set. And we abstract all of that by saying, well, the analyst will ask a question Q1, or propose a query Q1, or ask or interact in some way Q1 and get some answers out. That's A1. And then depending on those answers, depending on the results of the study, that same data analyst, or maybe a different data analyst if this one has published the results of her study, will then adaptively, based on those questions and answers, choose new questions and answers, follow-up studies, and so on. And so this process can repeat back and forth for a while. So as I said, our driving scenario in this work really was analysis of US Census data. The US Census Bureau publishes literally billions, tens of billions of statistics on the data of some 300 million people. And the Census Bureau has a legal mandate for privacy. So they have to protect privacy. That's the law. And therefore, we thought they would be receptive to ideas about how to do privacy-preserving data analysis. But the general question of how to do privacy-preserving data analysis is very old. It's a 55-year-old problem dating back to at least 1965 in the works of Stanley Warner, who gave a simple technique which we can now reinterpret from the perspective of differential privacy for collecting answers from people about embarrassing or even illegal activities. So this is maybe our sensitive question. How many people floss regularly? Or did this person floss regularly? So we're going to use flossing as our running example. And we have some kind of, so we still have some kind of intuition about statistics. So this is going to be, our intuition is if we ask the question of how many people in the sample floss regularly, we get an answer, it's not going to be very disclosive. But that's not always the case. So suppose, for example, that we say, how many members of the House of Representatives floss regularly? And we get the exact answer to that question. And now we follow up with the question, how many members, other than the Speaker of the House, floss regularly? Again, that's just a statistic. By itself, it probably doesn't tell us very much. But if you put the exact answers to the two questions together, you figure out whether or not Nancy Pelosi flosses regularly. Now, this little example is cute and it's contrived, but it's in fact absolutely fundamental. So there's a theorem called the fundamental law of information recovery or fundamental law of information reconstruction. And basically it says that overly accurate estimates of too many statistics is blatantly non-private. It will completely destroy the privacy of your data set. Now, what does overly accurate mean? Well, that depends on how many statistics you're getting. So those two notions have to walk sort of hand in hand. Good. And here's an analogy that I find useful. You know that small doses of radiation, say for X-rays for teeth and various other things, small doses can accumulate to cancer-causing amounts. Right? And you won't necessarily feel anything for any particular one of these measurements. And how many measurements you can take depends on the dosage. So you could clearly have more dental X-rays than you can CT scans. Okay? Okay. So let's move then. That's the scenario. So we're going to ask questions and get answers, and we're going to somehow or other do something. We can't answer everything accurately. That would be deadly. But we will do something. So what is it that we want to do? Well, first we have to say, what's our goal exactly? We know the setting, but what do we mean when we say we want to preserve privacy? This is Cecilia Helena Payne-Gaposchkin, and she was among the first women to obtain a PhD in astronomy, and she was the first person to obtain a PhD in astronomy at Harvard. And she ascertained the temperatures of the different classes of stars and estimated the great abundance of hydrogen in them, much more than there is on Earth, while doing the research for her dissertation, contradicting the belief at the time that the sun and the Earth had similar composition. So we want to protect her privacy. What does it mean to protect her privacy? Without a definition, we don't know what we're talking about. So what kind of protection should we be giving to Cecilia Payne? A natural candidate, especially if you know any cryptography, was articulated first in 1977 by the statistician Tordelinius. And what it says is that the data analyst shouldn't learn anything new about Payne by interacting with the data set. Okay. So she might be an extrovert, she might have published all sorts of things about her, she might have been covered in the tabloids, but the privacy-preserving data set shouldn't teach you anything you didn't know about her, specifically. So that was definitely the first thing that we tried, but if you take that view, then what is the point of a statistical analysis or a statistical data set? So to give you an idea, suppose I'm from Mars and I believe that all humans have 2 left feet. So in particular, I believe that Payne has 2 left feet. And now I interact with this privacy-preserving data set, and I learn that the vast majority of humans have 1 left foot and 1 right foot. I change my beliefs about Payne. I figure it's much more likely that she has 1 left foot and 1 right foot. And so the question is, has Payne's privacy been compromised? I've learned something new about Payne by interacting with the data set. Now, this is going to be a judgment call. There's no tablet set in stone that says whether this is or is not a privacy compromise. We decided it would not be considered a privacy compromise. And in fact, the reason for this is that we would have learned the same thing even if Payne had been replaced by some other random member of the population. So this is Henrietta Swan Leavitt, who was the first to note a relation between certain variable stars' peak brightness and the period over which that brightness varied. And that proved to be a very valuable means for measuring distances across space. So that brings us to the English language definition of differential privacy. It says that the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the data set. And essentially equally likely here means over randomness of the algorithm, not choice of the data set, but randomness of the algorithm. I will emphasize this point when we get to the formal definition. The differential privacy guarantee is very strong, and it says that even if the analyst knows the data set, the entire data set, and knows all of Payne's data, and the only thing that the analyst does not know is whether she's interacting with the sort of augmented data set that also has Payne's data, or the data set without Payne that otherwise looks identical. It's just missing the data of this one person. And with differential privacy, even an adversary that knows both data sets in their entirety would still never be able to distinguish, no matter how much computation she does, how much extra information she gets from other sources, would never be able to figure out retrospectively which of the 2 data sets was being used in the analysis. And as I said, what's the source of uncertainty when I say essentially equally likely? That's going to be over coin flips of the algorithm. So just to focus on that a little bit more, suppose you have a fair coin. A fair coin means that when you flip it, you get heads with probability a half. I'm going to say, instead of saying a half, I'm going to say 500 over 1,000. Still a half. And now I could have instead, now consider, we have this fair coin, now consider a very slightly biased coin. And this slightly biased coin has chance 501 over 1,000 of coming up heads. So it's a little more biased towards heads. Now, suppose I choose one of these coins, and I don't tell you which one I've chosen. And then I flip the chosen coin, and I tell you the result. The result, of course, is either heads or tails. What we're saying when essentially equally likely is, the probability of outcomes of heads or tails is nearly the same, independent of which coin I was actually using, the slightly biased one or the unbiased one. So what we're saying is that given one or even several flip outcomes, the adversary could never figure out which coin you had. That's what we mean when we say, even knowing both data sets, the adversary wouldn't know which data set was being used. Now, with such a strong notion of privacy, it's almost counterintuitive that you could do any useful data analysis whatsoever. And if you're skeptical, that's fine. It's reasonable to be skeptical. I just want to make a point for those of you who are familiar with some concepts from machine learning. So in machine learning, we analyze given data, which is of course redundant since data means given. We analyze a training set in order to learn something or other about how to distinguish positive outcomes from negative, instances that will have positive outcomes from instances that will have negative outcomes. But the point isn't to figure out what's going on with the training data. We have all the answers for the training data. The point is to generalize, to extend to unseen examples. I want to learn what's going on so that when a new loan application comes in, I can say, is this likely to be somebody who could repay or not repay? I should know what the story is. And what's known is that if your method for training is not impervious to small changes in the data set, then this business of generalizing to unseen examples can't work. So the business about being robust to small changes in the data set is called stability. Stability preserves privacy, as you will see, but it also prevents overfitting to your data. And so it turns out that privacy and generalizability are actually aligned. So while it is true often that you have a privacy utility trade-off, there's a limit to that. If you don't have the ability to have privacy, you won't be able to extrapolate. Okay, so now we've seen the English language definition of differential privacy. Now we'll give the formal definition. So I need to tell you about a couple of terms first. Our algorithm is going to be called M, also called a mechanism. We need the notion of what we call adjacent data sets. So data sets X and Y are adjacent if they're almost identical, but they differ in the data of just one person. So in the example I gave you earlier, the data set with pain versus the data set without pain, they are differing in the data of just one person. So that's what adjacent data sets are. Now, the algorithm does something and it produces outcomes from some space. And if you look at any subset of those, that's called an event. And finally, differentially private algorithms come equipped with a parameter. And the parameter is set by the person who is running the algorithm. The parameter is typically called epsilon, and it discusses how privacy preserving the algorithm really is. So if epsilon is very small, there's very little privacy loss, that's very private. If epsilon is large, there could be a lot of privacy loss. But there is this number, and you can play with this number to achieve perhaps the privacy utility trade-off that you need for your work. So armed with this, the algorithm M gives epsilon differential privacy if for every pair of adjacent data sets, no matter how nastily chosen pair of adjacent data sets, X and Y, and everything S that you could possibly observe by running the algorithm, the probability when we see this outcome when we're running on database X is very close to, and I'll get on to that in a minute, the probability that we see that outcome when the actual database is the adjacent Y. Why are there probabilities here? Because remember, my algorithm flips coins. So when the algorithm flips coins, there's not just a single possible outcome when it runs on X. There's a space of possible outcomes when it runs on X, each with its own probability. The role of X and Y is completely symmetric here. So we have this inequality, but we also have the same inequality if we swap the roles of X and Y. Now, epsilon, as I said, it controls like how much privacy loss there could possibly be. So this is the privacy loss bound. And as I mentioned, the randomness is introduced by the algorithm. That's where the probabilities are coming from. Now, e to the epsilon, when epsilon is small, is approximately 1 plus epsilon. So what this says is that these probabilities are very close. When epsilon is small, 1 plus epsilon is close to 1. These are very close. Notice that saying that the algorithm M is giving us differential privacy, notice how I didn't care what the adversary knows now or in the future, or how much computing it gets to do, or what other sources of information it may have access to. Just like with those coins, the adversary knew that one of my coins was 500 over 1,000 and the other one had bias 501 over 1,000. I don't care how much thinking it does. From just a couple of coin flips, it really doesn't have anywhere near enough information to figure out which of the two coins is really the coin that's being used. Same thing here. Oh, how far did this go? Okay, sorry, it seems to be advancing on its own. Okay. So with this definition, you can learn things about people in the data set. It's okay to learn that, the vast majority of people have one left foot and one right foot. It's just that what you learn can't depend specifically on any individual in the data set. If you changed your entire data set, then you could learn something new. If you switched from only having Democrats to only having Republicans, you would have different statistical things that you would learn. You expect that. But what we want is that at small perturbations, you don't see a difference. And so you can learn things about pain, but there will be things that are true of the population as a whole. And you could have learned them even had she not been present. And that aspect lets us disentangle the teachings of the data set as a whole from what is learned about an individual. Here we have a language for saying we're learning about the data set as a whole, and we're not learning in a formal way. We are not learning about any individual in the data set. So in particular, notice that knowledge can cause harm. So maybe studying a data set, we learn that smoking causes cancer. And smoker S is known to smoke, and smoker S's insurance premiums go up as a result of this. Now, the same things would have been learned whether smoker S is not in the data set. That was, I didn't even say smoker S was in the data set. We'd learn the same things either way. So the insurance premiums would go up even if this particular smoker is not in the data set. It has nothing to do with being in the data set. And my claim is that learning that smoking causes cancer is the whole point of a medical data set. because when we learn that certain actions are harmful, we can take steps to try to stop taking those actions. So in particular, smoker S could enter a smoking cessation program. So let's go back to the needle and the haystack. Differential privacy hides the needle. If we have sort of X as the data set with the haystack and the needle, and Y is the haystack without the needle, then we're going to learn the same things about our population, whether the data set is X or the data set is Y. And that's why this is entirely the wrong technology if you're looking for the needle in the haystack. Why did we choose this? We chose this in part because the outliers who are hidden by differential privacy, the outliers are often the people who most need privacy protection. Any notion of privacy that's just great for the average person, but terrible for the outlier, is not really giving you what we would consider a meaningful notion of privacy-preserving data analysis. The hope is that giving this kind of strong privacy would encourage people to allow their data to be used for useful things, like finding out that smoking causes cancer. So we were hoping that having such kind of power would encourage people to opt in. When you have more and more people opting in, you get more statistical power. This is a good thing. Now, there are certain properties of differential privacy that flow entirely from the definition. That is to say, any differentially private algorithm, anything that satisfies the definition that I had there on the slide, a couple slides back, will have these properties. So independent of how you implement differential privacy, these are some guarantees. One of them we've already talked about. This is the question about being future-proof. Remember we said that what the adversary could figure out had, like the differential privacy guarantee was completely independent from what the adversary happened to know or not know. Now or in the future, it doesn't matter when the adversary learns more things. Okay. So it's future-proof. It composes gracefully and automatically. That is to say, remember at the beginning, early on, in the fundamental law of information reconstruction, we said that overly accurate estimates of too many statistics is blatantly non-private. There's a big gap between a couple of statistics and the too many that give you blatant non-privacy. What is the too many? What does it take to get there? So differential privacy lets you understand how your privacy loss is accumulating over multiple queries so that you can either increase or decrease the privacy budget so that you're leaking less and less privacy, or maybe even cut off interaction with the data set completely. So at worst, the privacy losses will add up, but things are a bit better than that. So as a result of this, differential privacy is programmable. That means that, think about how programming is done. One doesn't just sort of sit down and just write an entire complex system, line after line after line. Typically, one breaks it up into pieces, building blocks, subroutines, whatever, and then using creativity and thoughtfulness combines these building blocks in creative ways in order to carry out some complicated action or analysis or build some system. And kind of that's what good programming and good algorithm design is all about. So the same thing happens here, that we can build small differentially private computational primitives, and then the whole goal in privacy-preserving data analysis is when you want to do something complex, you hook up these small pieces in just the right way in order not just to minimize standard resources like time and space, but also to minimize cumulative privacy loss. It's just another resource. So I'm going to give you an example of one simple technique. The general flavor is symmetric noise addition. So our question is going to be, what is the population of Washington, D.C.? Now, here, this is taken from the Census Bureau website. Population estimates July 1st, 2017. Okay? And the number that's given there is 601,723. So here's the line, the real line of numbers. And there's the true count as recorded in this data set. I'm just turning on my pointer. Okay. So this is the actual value. And now when somebody says, tell me, what is the count? What is the population of Washington, D.C.? Well, we're not going to answer that directly. We're not going to answer that with this exact number. So how do we perturb the answer, and how do we choose our randomness for perturbing the answer? Notice that if one person opted out of the data set, instead of being at 601,723, the population would be at 601,722. So that's shown here. So intuitively, and of course if we added one person, we'd have one more on the other side. So intuitively, what's going on when we add the noise is we're trying to hide the difference between 601,723 and 601,722. That's what it's going to mean to say you would have gotten essentially the same answers or the same probability distribution on answers if somebody had opted out or refrained from joining the data set. So we're going to add random noise to obscure the difference. And here's just some kind of cartoon showing the probability distribution on the answers that we're going to give, when the truth really is 601,723. So maybe that's supposed to be centered right here. That would be the most likely answer, but there's some probability of answering 601,722, 601,724, and so on and so forth. Now, how fat should those curves be? Do you understand what I mean by fat in this picture? How spread out should this be? Can this be a sharp peak, or does it have to be a little fatter than that? Well, the fatness that is required depends on two important quantities. One of them is called the sensitivity of the counting query. Sensitivity is not an emotional issue. It's how much can the data of one person change the outcome of the function. If I look at two adjacent data sets, by how much? What is the worst case over all pairs of adjacent data sets by which these two, the function will differ? So if you think about a counting query, the addition or removal of one individual can change the count by at most one. How many people in the database like to eat muffins? Well, you know, there's some number, and if you take a person out, that number might go down, but only by one. If you add a person, that number might go up, but only by one. So the sensitivity is just one, and that's that capital delta here. Now, the second, and notice that this is a function of the question. I'm not asking about a particular data set. I'm saying how, this is just of a counting query, any counting query. How much can the value change? So I can answer that question without looking at the private data. Okay, and the other question is, how tightly do we want to restrict the privacy loss? As I said earlier, a privacy loss that is very small is good, more private. And a privacy loss that is large is less private. So, and I said it's under the control, it's a parameter, it's under the control of the algorithm. So, so to how tightly we want to restrict, that is captured by what is the value of epsilon. And the answer to the fatness of the curves is more or less the sensitivity of the function divided by epsilon. So why is that why are those kind of why is that the right form? I didn't give the absolute fine details yet, but why is that the right form? If adding or deleting one person to the database could wildly change the value of the function, then we need very fat noise. So the fatness will have the sensitivity in the numerator. Bigger sensitivity, bigger numerator, fatter curve. If we want very, very good privacy, then again, we want to smear that probability distribution out. If it's too narrow, if it's a sharp peak right over the actual value, we're not going to be able to hide much. And when we have epsilon in the denominator, a smaller epsilon means, again, a fatter curve. So that's the flavor of it. The actual correct answer here is what's called the Laplace noise distribution with parameter delta over epsilon. So you can look up this distribution on Wikipedia and see why that's the right answer. So that's all I'm going to say. This is just one example of how to do something, release the value, a real valued function in a differentially private way. There are others, and there are things that you can do when you're not producing real valued functions. Maybe you're producing little data models or little synthetic data sets or some large collection of statistics. So there are different techniques that you would use for these sorts of things. Now let's talk a little bit more about this parameter epsilon, because when we did this, we said, well, epsilon is a policy decision. We're giving you the algorithms, but you, the data curator, or the people who are using this for your practice, you know what is the right degree of privacy that you need. And of course, what is the question, the first question that we got every single time we would talk about this? What should epsilon be? It's like, we don't know. But let's talk a little bit about epsilon. So the most important thing is that a small epsilon is a happy epsilon. So it doesn't matter what the algorithm does. If epsilon is small, you're getting good privacy. Like, I don't care about the specifics of the algorithm. Knowing that epsilon is small is good enough in terms of privacy. All happy epsilons are alike, but an unhappy epsilon is unhappy after its own fashion. Some high epsilon algorithms are just awful, like obviously awful. One of them, two of them, might be very, very lucky if you happen to use it just once in isolation, even though epsilon is big, maybe nothing terrible will happen. But of course, nothing is ever used in isolation. The name of the game always is more statistics, higher levels of composition. Remember, we started with the census with its tens of billions of statistics, or uses in industry, monitoring, your use of emojis on your phone. Things like this, just tons and tons and tons and tons of measurements. Nothing's ever in isolation. And the way that that ends up getting dealt with, and I'm just going to say a tiny bit about this, is, well, there are two ways. One is the introduction of some techniques which are called amplification techniques. We won't have a chance to talk about them, but they're kind of algorithmic methods. The other is to relax the definition of differential privacy. We saw that it was a very strong definition, and the question is, can you relax it in ways where it's still giving very meaningful protection, but you can get more utility out of it? Interesting. Okay. So I think I have about 2 slides on this. So if you get lost here, don't worry, you can get back on in a moment. Remember, we said that the algorithm is randomized. And we said that epsilon bounds the privacy loss that we allow when we're running the algorithm. It turns out that when, consider a pair of adjacent data sets, X and Y. And suppose we're running our algorithm when the database is X. And suppose, now remember, the probability of seeing any particular outcome is essentially equally likely whether the database is X or Y. Some outcomes will be a little bit more likely when the data set is X. Some outcomes will be a little bit more likely when the data set is Y. But in a differentially private algorithm, all outcomes that are possible under X will be possible under Y, and vice versa. So again, suppose that the real database is X. Then if we run it and we get an outcome that has a higher probability on X than on Y, since X really is the truth, that turns out to be what we call a positive privacy loss. But we might, with almost the same probability, not quite, we might get an outcome which happens to be more likely when the data set is Y. So that's almost like throwing the adversary off the scent of the truth. Oh, it's more likely that it's Y. So the privacy loss can be either positive in that first case or negative in the second case. Now, I don't know if you've ever heard about random walks where, you sort of start in one spot and you flip a coin, and with some probability, probability of half, you take a step to the left, and a probability of half, you take a step to the right. And you do this and you wander around. If you look at where you're likely to be after a pretty long time, well, it's kind of got a nice bell sort of shaped curve, a normal distribution. So because, that stepping left and stepping right, that's the same thing as having positive privacy loss and negative privacy loss. And if you look at something that can give you positive versus negative loss, and you run it many, many, many times, there will be some rights, and you'll get this kind of, you're going to stay near the expectation and not wander very far. And you can make that your definition of what you mean to be differentially private. So it's a relaxed notion. Very, very roughly, in this thing called concentrated differential privacy, the privacy loss is itself like a bell curve. And so, you're most likely to have a privacy loss of epsilon. If you don't, then it's really likely that your loss will be at most 2 epsilon. And if it's worse than that, it's still very, very likely that it's going to be at most 3 epsilon, and so on. Okay. And that's like with a normal distribution. What's your chance of being 1 standard deviation, 2 standard deviation out, and so on? So it's a relaxed notion because there's no absolute guarantee you will never be more than epsilon. It's just more qualified than that. So this is what we're comparing it to. And this is why it's a relaxation of the original definition. And this is the variant of differential privacy that's used in the 2020 Decennial Census. It was tailored to huge levels of composition. All right, so now we can talk about differential privacy and the 2020 Decennial Census. So differential privacy is now widely used in industry. And I don't want to be too US-centric. Every 10 years, the US does a decennial census, a 10-year census, and it does what is supposed to be, and of course never actually is, a complete enumeration of the public, of the people living in the US. And, so this is John Abowd, the Chief Scientist and Associate Director of Research and Methodology at the US Census Bureau. And Abowd wrote that they had discovered, based on their own testing, that it in turn was based on those reconstruction techniques from the fundamental law of Reconstruction, that the techniques that were used to ensure privacy in the 2010 census no longer suffice. What changed? I would say 3 things changed. 1, Reconstruction science is just better. Like it started, it's better and it's well known. People have a lot of computing power. And there's a lot of what we call auxiliary information. This is other information that can be used to help you, public information or commercial data sets or things like this that you can use in conjunction with a reconstruction to re-identify individuals and in particular figure out, say, their self-reported race and ethnicity. So they launched such an attack on their own published statistics. And they concluded that they needed to make a change. Remember, privacy is legally mandated. So they took it very, very seriously. Okay, so as Abeld says, we fixed this by using differential privacy. Was there a happy response to this? No, not necessarily. And we will talk about this. For one thing, privacy became political. So the state of Alabama filed a lawsuit against the Commerce Department trying to stop the use of differential privacy. They were joined by a large number of attorneys general from other states, almost all of whom were Republicans. One of the judges in the 3-judge panel, all of whom were Republican, one of the judges said, I don't understand what's going on here. Is this Democrat versus Republican? I just don't understand. Tell me the truth. Okay, so they lost their lawsuit unanimously. And they decided not to appeal to the Supreme Court. But there was huge political activity. Okay. And now I want to make a couple of other remarks. Privacy, noise was injected for the purposes of ensuring privacy in census data since 1990, when techniques such as so-called swapping and imputation were introduced. It was sort of known abstractly that this was going on, but the details, like the details of the swapping algorithm, were kept secret. Why were they kept secret? Presumably security through obscurity or something like that. But there was no rigorous proofs of anything underlying it. With differential privacy, the algorithms are public. So now suddenly everybody knows that you're messing with the data. You can't just pretend that this isn't happening because the techniques are completely public. There were undercounts. There are always undercounts, particularly of the poor, people of color, and children below 5. The undercounts were severely exacerbated by the pandemic. The noise that's introduced by the undercounts is most likely very large compared to any of the noise that's being added by the differential privacy. But that's what happened. Okay. And there are also overcounts. So you might have, say, a wealthy family that owns 2 homes. One person in a couple answers the census here, doesn't realize that the other one is answering it there, and you get overcounting. Another thing is that the Bureau didn't feel that they could just release noisy counts, because the noisy counts might be sort of inconsistent in some way, or you might have negative counts in some very sparsely populated area. Why? Because you're adding symmetric noise, and if you start with a small number and you add noise, well, with probability of half, you're adding negative noise, and if it's, at all chunky, it'll give you a negative number. So that wasn't considered acceptable. Plus, the Bureau had in later, like, what I can only describe as bureaucratic reasons, and I can try to reconstruct more details if there's a question, they had to produce essentially synthetic data, like things that looked like people, which would then get entered into a pre-existing, from their own past, a pre-existing tabulation system. And the outcome of the tabulation system is defined to be the counts. So they had to take these things which had some negative numbers and maybe some inconsistencies, and they had to make them look consistent and non-negative. Now, if you keep your total fixed and you have negative numbers here, you gotta move some people from populated areas out to nowhere. So it messed some things up, and that was in my, I was very sad to see that that was what they did. That was called post-processing. I wouldn't be surprised if post-processing will disappear at some point in the future. But so now you have these numbers that don't all make sense, that at very fine levels of geography have quite a bit of error, but if you aggregate up just a little bit in their particular hierarchy, then they start looking quite good. But a lot of people who use census data use it at very fine levels of geography. They're used for everything. They're used for thinking about schools. They're used for thinking about where the helicopters or the emergency helicopters should be stationed. They're used for figuring out school districts, legislative districts, and so on and so forth. So the task for all of the parties, both the Bureau, which was doing this monumental effort to bring rigorous privacy guarantees to the census on a scale that just hadn't been seen before. So their task was gargantuan. And then the users and the consumers are confused by what they see. They don't know how to work with things that have been produced by differential privacy. They're probably often using off-the-shelf software that just, it's just not happy with some of the kinds of things that it sees. Okay. The task was very, very hard. There was intense pressure on the Bureau for accurate numbers at very fine geographical levels. It's very important also for the Bureau to know what are the questions that need to be prioritized. There's privacy budget. We want to say that there's going to be a cumulative privacy loss of blah, blah, blah. We can spend much of that in one place and a little bit elsewhere. Where should we be spending our budget? When the Bureau tried to get this kind of information from the user community, the stakeholders, they had no idea what they were being asked. I would not be surprised if the Bureau got very, very little response to that sort of question. And all of the pressure on the Bureau is for more accuracy, more accuracy, more accuracy. There's nobody whose job it is, other than the Bureau itself, there's no one whose job it is to defend privacy. So all of the pressure goes in one direction, and the Bureau kept increasing and increasing the privacy budget. Okay. There's an issue that came out very recently, this month or last month, of the Harvard Data Science Review that has articles from people at the Bureau, experts in differential privacy, people from the user communities, and so on. Lots of different perspectives on what happened, what is needed moving forward, and it's a very rich source of interesting information. And just sort of finally, that was kind of differential privacy in the US Census. In general, it's a very exciting time for differential privacy. It's absolutely pervasive in industry, and its use is growing. Apple, Google, Microsoft, Facebook, LinkedIn. So for example, a colleague, Abradip Corta, was very excited that next word prediction for the Spanish language Gboard, which is Google's keyboard app, was trained on a data set just using differential privacy completely. It's being used in California for smart meter data analysis. It's being used by the IRS and the Department of Education. There was some interesting work not too long ago, classification of medical images, so we're starting to see it more in sort of more scientific settings. I didn't discuss models. I had this big centralized server and the data analyst interacted with that. But there are some, when Apple takes data from your phone, when they use differential privacy, they don't actually collect the raw data. They run something locally on the phone, which you can think of as putting differential privacy into the data, like a noisy piece of data now, a noisy datum goes from your phone to a server. And this is true for all of the companies. In the language of the companies, this is, quote, pushing the trust boundary out to the client. Translation, they have much less liability for what happens to it because privacy has been rolled into it before it comes to them. But that comes at an accuracy cost. The privacy utility trade-off is much worse there. So there's a new model called the shuffle model, which has been proposed, where there would be some kind of, something like a Tor router or something that would shuffle all the responses that have been randomized. And then when you do this, there's some beautiful tricks you can do to show that, wow, your accuracy looks just like it does in the centralized model, just about. There are new amplification results. Remember I said that sometimes we work with this stuff by changing the definition. Sometimes we do it algorithmically, so there are new amplification results that I found really exciting in the world of privacy-preserving gradient descent or projected gradient descent, which is a key step in deep neural net training. Also, especially given light of what's been going on with the census, when you work with noisy data and you compute various statistics, you get biases. It's not all just counting where the noise leaves things unbiased. And so there are new techniques being developed for bias correction of statistics on noisy data. And there are applications of differential privacy even when privacy itself is not a concern. And in particular, it provides a defense against what's known as p-hacking or overfitting. We call it adaptive data analysis. Okay. Thank you.